Hi, we are the Orbital ATK team. I'm Justin.
I'm Justin as well.
I'm Tyler.
And I'm Nathan.
We are working with Orbital ATK and working closely with our sponsors, Will, Eddie, and Mary. I'm just going to go over quickly what we will be covering in this presentation. We'll start off by doing a brief overview of the company we are working with, and then we will discuss the problem that we are tasked with solving, tell you a little bit about the development environment, our project schedule, and then we'll take a dive into the data analytics that we were able to capture. And at the end, we'll do some demos about encryption and different network configurations that we were testing, and then kind of sum all that up and tell you what we learned in our experience throughout the project. So Orbital ATK is a leader in aerospace and defense. They deal with things such as flight systems, defense systems, and space systems. And more specific to our task was embedded software. And the branch we're working with right now, they only use single isolated nodes, so they wanted us to look into a mesh network that had multiple nodes communicating with each other running an OS.
Alright, so just some brief terminology that most of you will probably know. When we say node, we're talking about just a piece of physical hardware that likely has sensors that can communicate with other nodes. A mesh network is a communication network made up of a bunch of radio nodes that all work together to transport data to and from a client and then to and throughout the network. Internet of Things, or IoT, as most of you probably already know, is just a network, is the idea of a network of physical devices that each have some sort of embedded electronic that allows them to communicate and connect with each other. Alright, so our initial problem was we needed a way to detect movement or just some sort of, any sort of changes in some sort of field or military base or maybe battle situation. And obviously this needed to use secure network traffic, and we needed a way to monitor this network that we have so we can monitor the data that is coming through and to the network. So our initial statement, which serves as our solution to the problem, was we needed to create a self-organizing, unified mesh network. And we were initially tasked with targeting the CC2650 STK board, but that actually changed throughout the semester, and so now we are targeting the Z1 board. And some of the data that we could transmit through the network was accelerometer, magnetometer, and light intensity data. And obviously we needed to use encrypted traffic so bad guys couldn't hijack our data. And we needed a way to monitor the network so we could gather analytics about the network as well as the data from the sensors. We also had one sort of stretch goal, and that was to support a single node command message, and we would have liked this to have a max latency of around 1 second from transmission to the node processing of the message.
Okay, so I'm going to talk about the environment that we're working with, and there's 3 main components to it right now. And the first one is Kuja, and Kuja is a network simulator that we use to get analytics from the networks that we would set up. And Kuja itself comes on the Kentucky repository, which you can pull from GitHub. And then on top of that, we were using Ubuntu to contain all of that stuff. And so for our development stack, we mostly had Windows and Mac computers that would load up a virtual machine with Ubuntu on it, and then we would pull the Kentucky repository. And in the beginning we were using Riot, but as you see it's crossed out. We ended up changing that partway through this semester, and now we're only using Kuja with Kentucky.
So next we'll talk about kind of our schedule as the semester progressed. In our first 2 sprints, we were focused mostly on setting up our environment. Riot and Kentucky didn't really want to mesh well together, so it took us a long time to figure out the problems and kind of what operating system we could load them both onto so that we could compile and run them both within one environment, instead of having to transfer back and forth between systems or anything like that. In our third sprint, we got everything working together, and we were focused more on actually building the operating system, the messaging system for our nodes. What we came upon was kind of a series of problems that we couldn't really work around. Riot and Kentucky, Kuja, the emulation environment, didn't like to work well together. So eventually we ended up scrapping that and just focusing on Kentucky for our operating system. So finally, in our fourth sprint, we did a lot of work, and we got Collect View working, which is a way to view metrics about your network. We got encryption working. We added a second border router to the network, so that way we could support more nodes and have less of a power draw on specific nodes. Just made it more efficient. So progress and what we've done over the semester. Kind of a rehashing of last slide. So we did a ton of research, in especially the first two sprints. We set up our environment. We completed a lot of tutorials, learned a lot of things about IoT devices, the different operating systems for IoT devices. We switched our focus from Riot to Kentucky. We found the correct board that worked well between the two. And finally, we found the correct board that worked just well with Kentucky. We collected network analytics, and we were able to emulate the network within Kuja. So encryption. Encryption is important for Kentucky and UDP, or networks in general, is because most networks have a way of verifying like who is saying what. Usually there's a password to join the network, something like that. But UDP doesn't have that, partially because it's for very small devices that don't have a lot of RAM or computing power. So that's why we needed it. Otherwise, people could just join the network, basically copy the messages that were sent out, spoof them, and just kind of overload our network with a whole bunch of false information. Encryption was completed in our last sprint, and hardware acceleration is built into a lot of the boards that's supported by Kentucky, but it's not supported by Kuja. So the real world numbers that we get and the numbers that we get from Kuja could differ a fair bit. And Kentucky supports up to 128-bit encryption. So here's an example of our network simulated within Kuja and it working with its encryption. In this one, you have number 1. The first node is actually the border node, so that's where all the information gets sent. The node number 6 is the unencrypted node, the node that's trying to kind of work within the network. It's a false node. And 5, 3, and 4 are nodes that are encrypted. So in this browser, you can see the information from our border router, and you can see the border router only detects the encrypted node that's next to it, which is neighbor 5, route 5. It doesn't actually pick up the 6th one because it can't talk to it since that one is unencrypted. In the next slide, I kind of changed up the network a bit to work around it. And then finally, we got it working, and you can see it connects with all the encrypted nodes, yet moves around the unencrypted node.
Okay, so I'm going to talk about network configurations that we worked with, and we tested 4 different configurations recently and tried to get some information and see which ones are more ideal for which types of scenarios. And so on the left here, we have a 36-node network with all these yellow nodes you see are all client nodes, and those are sending data to this green node, which is a border router, which is where we actually can visualize the data. And the difference on the right side is that we have the same network, except we have 2 border routers, which should speed things up. And then these two. We set up a pseudo-random network. If we set it up randomly, there might be like gaps, and they might not even be included in the network if they're too far away and outside of the radius. So we made it more random than the square grid. And on the left side, we used 1 border router, and on the right side, we used 2.
Right, so like Tyler mentioned, we use 36 was the number we were able to get to, and this was because the Z1 board has a max number of routes and max number of neighbors. So we were able to play around with those numbers a little bit to create the biggest grid we could, and we had it set to 32 routes and 4 neighbors. And the reason we could only go that high was because the Z1 board is limited in memory, so when we change those numbers, we use up more memory. We have to make sure that we fall in the category of the memory constraints. This is some of the data we were able to collect through CollectView, and when using 2 border routers, the biggest thing that stands out is the average number of hops is much lower, and this is because there's a shorter path to the nearest border router. A number of hops is basically just referring to how many jumps it has to go through to each node to get to the final path destination. And then also the average routing metric was also lower with 2 border routers, and that's basically measuring the cost of the messages. So when it has to go farther, it has a higher cost per message. So obviously when you have 2 border routers, it doesn't have to go as far. So the cost is less, making the network faster and more efficient. And then it also has a direct effect on power consumption, which Justin will touch on.
So looking a little bit more into the average CPU power, for the square network layout with the 1 border router, we had 0.057 milliwatts of power. When we added the second border router, that actually decreased slightly. This is likely due to the fact that on average, the distance, which is equivalent to the number of hops that each message has to take from the node to the border router, is less than with the 1 border router. So we see that decrease in power usage. When we compare that to the random layouts, we actually see the random layouts are a bit higher than the square layouts. This is likely due to the fact that they're less efficient, and there are some nodes that are much closer together and far away, and so they will likely have to transmit through more nodes to get to the border router.
And to summarize what both Justins just said, was essentially what we found was that the square grids seem to be more ideal in the fact that if a node drops out, like let's say number 12 just dies, 7 can just go around that and like get straight to one a slightly longer way. But if you're in a random network and a node dies, you might completely isolate the nodes around it. So the square grid's better in that regard. But also, the square grid was more consistent in the number of hops we see, whereas if you have a random network layout, then you really have no idea how well the nodes are going to be scattered. And we also found that in both configurations, having an extra border router decreased the amount of hops it usually takes to send a message. So more border routers is usually better.
So next we're going to talk about network repair. Network repair needs to be triggered when a node either drops out or is added to the network. It makes sure the border router knows how it can get and talk to that router and that node, and how that node can get back to the border router. So by default, network repair is triggered once every 10 minutes over Contiki, and it's very important because it can leave the entire network vulnerable. If network repair isn't triggered after a border or after a node dies out next to the border router, then it could potentially lose a lot of information that's being sent to it. So you kind of want a happy medium of when to repair the network and when not to. Part of that is just because the majority of the power consumption of each node comes from transmission. And so by every time you try to reconfigure the network, trigger the repair, it takes a lot of power to do so. So here's just an example of network repair real quick. In the first slide is the network, everything's fine, happy. It can get to node 5 can talk to the border router. The border router is the node number 1 in this example. In the second example, or in figure B, the node number 3 drops out of the network, so now they can't talk to each other, and then figure C is just how the network would reconfigure itself, so it could talk to node number 5.
Okay, so I'm going to go over how we actually ran those tests and found that data that we showed you earlier. So this is the environment that we're working in, and this is just kind of the blank canvas where we can add different types of nodes and see how they interact with each other. And so we've got some nodes set up here. The yellow ones are, again, client nodes, and the green one is the border router. And so the first thing that we did was we wanted to make sure that everything was within the radius of each other. That way they can talk, because kind of need that. And then so the first thing that happens when you start the simulation is that the network starts to configure itself and figure out the paths to get to all the client nodes. And so to actually start collecting data, we have to click on our border router and then go to the Collect View button over there. And that gives us this nice window where it houses all the information that we can collect from the network. And it doesn't initially have any information in it because it takes 60-second intervals to actually have the client send information to it. So it's not like you're going to get everything all at once. It's going to slowly keep accumulating information. And so after we've got some information, this was consistently what we were seeing with average power consumption. All the nodes in the network were using about 60, or kind of around 56, that area. And most of that is being used by the radio listen. As you can see here, almost all of it is being used by the listening on the radio network. And another interesting bit of information we can get is the network graph. And basically, every black dot you see there is corresponded to a node. And this diagram is what the simulation has gathered and how it actually sends the data to the different nodes. And this is the initial data. This is the data from when the network initially starts. These aren't the fastest paths that you could actually take to a node. Like you can see here that it would actually, if you wanted to send data from the border router to node 12, it would actually go through a fairly bad path instead of just going directly to it because they're within the radius. And as the network goes on, then this gets fixed out and it'll find the fastest paths that way. And probably the most important information we got was in this node info tab. And this showed us a wide variety of data for every single node in our network. And it also gave us nice averages, so we could see the average number of hops and the routing metric. And the ETX is, it's a term used in mesh networks, and it corresponds to kind of what Justin was talking about earlier, the cost of sending a message to that node. And you want lower numbers in that regard. Yep. Okay.
All right, so when working throughout this whole process of creating a mesh network, we ran into our fair share of problems. Initially, the majority came when working with Riot and just trying to cross-compile, and we ran into tool chain issues and compiler bugs. But once we were able to change our focus to Kentucky, it really sped up our progress, so we didn't have to worry about cross-compiling anymore. And then when working with finding the right board, we settled on the Z1 because it had compatibility with Kuja and Kentucky. And it, like I mentioned before, it is limited in memory. It has 92 kilobytes of flash memory and 8 kilobytes of RAM. So we didn't have a lot to work with, and to get around that issue, we had to delete unused modules. When I say modules, basically just different functionalities of the board, like UDP messaging, having the client view work within the nodes, things like that. So we had to decide what we needed and what wasn't necessary at the time. And then at first, when using Collect View, our data wasn't displaying, and we found this to be we had to make sure the port numbers were consistent between the border and client nodes. And even so, we still only got it working on 2 machines. That kind of ties into some of our risk. Was Collect View can be somewhat unreliable, where some days it would work and then the next day it would just stop working, so we would spend our nights trying to figure out why that was the case, when really we would have been like to make more progress on our actual problem. And then one risk that we will always have to deal with in this project is the Z1 board not having a lot of memory, because as we add more functionality to our network, we have to make sure that we don't go over the threshold of how much it can take. So we kind of have to choose wisely what we are going to add to our files. When looking over our whole progress and our work that we did on this project, we really found the most important part was communication, and through the second half we started to ask more questions more frequently with our sponsors, and that really helped us, and like we were able to see actual progress. When instead of banging our heads against the wall for 6 hours, we were just asked the question and we were able to move on, and that was really good for us. And then definitely switching our focus from Riot to Kentucky helped a lot as well. And we were able to just have more of a single-minded approach and have to worry about cross-compiling or what boards we were going to use, so we could make more progress that way. One thing that we do wish we would have had time to get to was sending actual sensor data throughout our network instead of just like the generic messaging that we were using while testing our network. And then we also did not get to any of our stretch goals.
So, in our last slide here, we're going to talk about what would we do would we be continuing this project. So, the next steps that we'd work on would be getting the sensor alerts working, as Justin just said. After that, we'd try to port our software over to actual hardware, so that way we could see what or kind of the discrepancies between Kuja, the simulation environment, and the real world numbers. That way we could get more of a accurate view of everything happening. And then finally, get a web server set up so each board router can send the information it has to a central location. So that way you could have multiple board routers set up and just view could view all the information in one location. So thank you guys for listening, and do you have any questions?
One little one, just because I didn't understand. Do you have the chart where it showed the power consumption?
Mm-hmm.
Sure.
Nope.
Do you want the
The bar graph.
Okay.
Yep, that one.
No, before.
No, the table.
So let's go.
Yeah.
One thing before you ask, this is a typo and it should be the
Okay.
same across all of them.
That was my question: is why is there an order of magnitude difference?
That was probably my fault.
Yeah.
But I had one more here. On the bottom line, the transmit power,
Yep.
I would have thought that would have been the smallest for the square two border.
Is it the same with that bottom right cell, where again it's an order of magnitude difference? Is that a typo?
The 0.29 as opposed to 0.02. Yeah,
Yes.
I believe that's a typo.
Okay.
Maybe, yes.
But
But
for
the-
Dean's question, I'm not exactly sure.
Yeah, I'm thinking transmit power should be better if you don't go so far.
Mhm.
Yes,
And it
yes.
seemed like in the square two border router, transmission should have been smaller.
It probably
It's
should have
the
been.
largest
Yeah.
one. Oh.
Yeah. That probably indicates that we need to do more testing and to average it out and doing that, so we don't have any discrepancies like that.
Yeah,
It also-
dealing with simulators and values this small, there could definitely be like some discrepancy in
Yeah.
it. It'd be best if we were able to run the tests a lot more than we were able to.
Yeah. One
Good
thing
question.
that could affect it too is sometimes when using two border routers, there could be some overlap. So we weren't able to completely eliminate that. So maybe it was, there's overlap, so it's kind of doing the same thing twice instead of just doing it once. There's that extra messaging coming in for both border routers.
And what you mean, or like just to kind of clarify that, when we have two border routers, each one kind of gets their own network, like subset of the network, and there can sometimes be nodes that end up on both networks. So that might be the reason. Can't verify it, or at least right now. But
Yeah.
good question.
Anything else? All right.
Right.
Well, thank you.
Thanks again.